Welcome to this lecture series in group theory. In this lecture, we'll be discussing the third isomorphism theorem, and the only thing we need to prove that is the first isomorphism theorem, and I don't want to recall it since we have done it so many times. Here are the problems. This will give us more perspective on the notion of quotienting in general, and this is a nice problem to see that two very different looking groups can be actually isomorphic. All right. So this is going to be a very short lecture. The theorem is as follows. Fix a group G with two normal subgroups H and K, and suppose H is a subgroup of K. So then clearly H is also normal in K. I'm not writing that. So one of the conclusions is that K mod H, which is legitimate since H is normal in K, is a normal subgroup of G mod H, and then the corresponding quotient is actually isomorphic to G mod K. So it's sort of like you can cancel off these things, just like in numbers A by B divided by C by B is A by C. That's kind of what it looks like. All right, so here is the proof. So consider the natural projection map G mod K. So this is pi. And clearly the kernel of this map is K. So yeah, let me spell out what is pi. Pi is just G going to GK. Kernel of this map is K, which contains N, and therefore what we saw, not N, this contains H, and therefore by what we saw in the revisit of the first isomorphism theorem, this map pi factors through G mod H and gives us a group homomorphism, which let me call phi. It's usually we would write pi bar, but let me just use the word phi. And this map is the natural projection map. It just takes G to GH. Let me not even give it a name. All right. So now what is the kernel of phi? Let us figure out what is the kernel of phi. So kernel of phi is those elements in G mod H such that, so okay, what is phi? Phi takes G goes to GK and this via this route, and G goes to first GH, and then it has to go to GK because this diagram commutes. So phi just takes GH to GK. That's what phi is. So this is for all G. Right, so kernel phi is by definition, I need more space. So this is by definition, this is equal to the identity of G mod K, but identity of G mod K is K. So this is all all GH in G mod H such that G K equals K, which is all G in K. So this is nothing but K mod H, all the left cosets of H that you can form using elements of K. So K mod H appears as the kernel of phi. Phi is a group homomorphism, of course. Therefore, this implies K mod H is normal in G mod H. So that part is there. Further, since K mod H is the kernel, the map phi further factors out to give us this quotient. And this one I will write as phi bar. So we are applying the first isomorphism theorem again. All right. So this is an injective map simply because we have factored out by the kernel of phi. So this phi bar is injective, and injectivity is usually denoted by this hook here. So that's how we denote it in a diagram. And now let us just notice that, first of all, the map pi is surjective. Surjectivity is denoted by double arrows. So pi is surjective. And if you factor out a surjective map, you again get a surjective map. That's a basic set theoretic thing. So this is also surjective. And we have further factored out a surjective map. So we again get a surjective map. So phi bar is surjective. So therefore, phi bar is an isomorphism from G mod H modulo K mod H to G mod K. So we have obtained an isomorphism, and the description of this isomorphism, well, it's going to look a little bit ugly, but there's a way to write it in which it doesn't look so ugly. So it just takes G bar K mod H to GK, where G bar denotes the left coset of H corresponding to G. So G bar is just GH. So that's what this map is. If you just figure this out, that's what that map is, because what is GH here going to via this map? This is the natural projection map for this quotient. So this goes to GH K mod H, and then that goes to pi of G, which is GK, because of all this commutativity. So basically that's the map. However, it is just remembering that these two things are isomorphic is one thing, but I think what one should really keep in mind is this diagram. And there's nothing to really keep in mind here, because you can just immediately prove this if you apply the first isomorphism theorem. It kind of falls out on its own. There's nothing to remember here. My point is that it is important to know what the isomorphism is rather than just knowing abstractly that these two groups are isomorphic. They're in some sense naturally isomorphic, whatever that means. All right, so this was a nice application of the first isomorphism theorem. And with that, I want to end this lecture. As usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.